So as we discussed in class, there are three consequences of this peptide bond resonance. So the first is that it restricts free rotation around that carbon-nitrogen peptide bond. And this results in a bond that is shorter and stronger and more rigid than a regular or your typical single bond would be. And so therefore, when we look at polypeptide structures, you only get rotation around this N and alpha carbon, and this angle is referred to as the phi angle, and then the alpha carbon and the carbonyl carbon, and this angle is defined as the psi angle. So in this slide, we see that angles basically determine protein conformation. So the shaded blue section highlights the fact that these bonds are planar and that there is no rotation around this nitrogen-carbon bond. So we see here the plane is formed by 6 atoms, 1, 2, 3, 4, 5, 6. So in this polypeptide, there are two planes. You have free rotation around the phi angle here, and then the psi angle, which is here. And so we can describe a polypeptide in terms of its phi and psi angles. Now, other single bonds in this rotation may be rotationally hindered, depending on the size and charge of the R groups. And so it's written here, it's depicted as if you can adopt any angle in this bond, but actually that depends on what the R groups here are. Here we see the planar groups in a single polypeptide. So again, this blue shading highlights the planar nature of these peptide bonds, and the consequence again is that this peptide bond here, 1.32 angstroms, is shorter than is a typical N to carbon bond, which is 1.46. So if we look at in general, some typical bond distances are between your carbonyl carbon and the oxygen is 1.24 angstroms. Between the nitrogen and the alpha carbon is 1.46 angstroms. Between the nitrogen and the carbonyl carbon is 1.32 angstroms. And then the alpha carbon and the carbonyl carbon is about 1.53 angstroms. So based on this conformation and the bond angles given here, a fully extended polypeptide of 100 amino acids would be about 360 angstroms. Now, steric crowding between peptide planes actually limits the number of structures possible. And so you don't really observe free rotation around those phi and psi angles. And that's because of what we call steric hindrance or steric crowding. And that is just due to the fact that two atoms cannot be in the same place at the same time. And so of these four structures, we see that the first two and the last one are not allowed. So these, when we look at the structures with the current psi and phi angles that are given, we see that steric hindrance is going to prevent this. So these two oxygen atoms are too close to each other. We have overlap of the amino carbons in the second, again, isn't possible. And then in the third, we see additional overlap between the oxygen and the hydrogen. So again, out of the three possibilities, only one of these is actually observed. So Ramachandran and his co-workers showed that it's convenient to plot phi and psi angles to show the distribution of allowed values in a protein. And so this is a Ramachandran plot of L-alanine. And basically what it is you plot your phi and psi angles, and then look at the allowed conformation. So basically we see three colors. You have your light blue, dark blue, and then yellow. Dark blue are angles at which there is no steric hindrance, and so the molecule is free to rotate in this area. Medium blue allows some unfavorable atomic contacts. Light blue, if you're really flexible in your bond angles, you can observe these. And then the yellow are strictly forbidden. Now, remember that alanine has only a methyl side chain, and so we could imagine that the phi and psi angles that it can adopt are going to be fairly broad. There won't be a lot of steric hindrances because the R group is so small. The asymmetry of this plot, so we see here there is a lot of blue here and not much blue here, is due to the stereochemistry of the amino acids. And if we were to look at the plots for other L amino acids that have unbranched side chains, they're going to be very similar. So allowed ranges for branched residues, such as valine, isoleucine, threonine, are somewhat smaller than alanine. So the glycine residue, which is less sterically hindered, has a much broader range of conformations, and the range for proline residues is greatly restricted because it has that large cyclic side chain. So again, glycine has a smaller R group. It's going to be less sterically hindered. It's going to have a broader range of allowed conformations, and there's going to be more blue. Proline is going to be very restricted. It has that really bulky R group, and you're going to have very little amounts of blue. And so on the exam, I might give you a number of different plots and ask you to explain to me whether or not those plots belong to an amino acid with a small side chain or a large side chain, and so forth. So peptide bonds aren't the only linkage between amino acids. Disulfide bonds are another one. And disulfide bonds are another form of covalent linkage in proteins. And it involves a crosslink between two cysteine residues. So here we see a cysteine residue here and a cysteine residue here. In general, they are strongly hydrophobic. Okay, so these are nonpolar. And under mildly oxidizing conditions, they form covalent bonds. So we see oxidation, we form these covalent bonds, so now you have a disulfide bridge, and then when you hit reducing conditions, you now see that that disulfide bond is really reduced to yield two cysteine residues. So these disulfide bonds can be cross-links within a single chain or between two different polypeptide chains. And what we see here is that these are disulfide linkages. We see one here between the alpha chain and the beta chain. We then see another disulfide bond here linking the two chains. And then we see a disulfide bond formed here within a single chain. Now, disulfide linkages are not typically found in intracellular proteins, but they are found in extracellular proteins, and that is because the environment inside the cell leads to reduced cysteines. Prominent local structures that we'll look at are alpha helix and beta conformation. Now, both of these are very stable structures, and they're common in a lot of different proteins. So first we're going to look at the alpha helix. And in 1951, Linus Pauling and Robert Corey used a modeling approach to determine possible periodic protein structures. And based on what they knew about peptide bonds, and then the X-ray studies of proteins that were done by another group on alpha-keratin, he was able to show that alpha-keratin has a regular structure that repeats every 5.2 angstroms. Now here's the model of a right-handed helix. And here, basically what we see is that this helix winds around an imaginary axis. So here's the amino terminus, here's the carboxy terminus. And we see carbons are in gray, R groups are in purple, hydrogens are in white, oxygens are in red. And this is a picture of the helix from the side. And then this is another representation that shows the hydrogen bonding that occurs between the different parts of the molecule. So one turn or repeat of the alpha helix is 5.4 angstroms, and there are 3.6 amino acids per turn. About 25% of all polypeptides are made up of alpha helices. And alpha helices can be made up of L amino acids or D amino acids, but you do not observe mixtures of L and D amino acids in a single helix. So in theory, there can be left-handed or right-handed helices, but right now only right-handed structures have been observed. So this is another figure that demonstrates handedness. And basically, if you look at your right hand, so what you want to do is make a fist with a thumb outstretched. So if you look at the right hand, the helix is spiraling up the right thumb in the direction in which the four fingers are curled. So this is a right-handed helix and it goes counterclockwise. In contrast with the left-handed helix, the turn is going to go clockwise. So again, in the left-handed helix, the spiraling up your left thumb in the direction in which the four fingers are curled. If it's left-handed, it goes clockwise. If it's right-handed, it goes counterclockwise. In addition to stabilization by hydrogen bonding, helices are also stabilized by interactions between R groups that are 3 residues apart. And here we see a space-filling molecule. These are the 2 residues that are interacting with each other. They are 3 residues apart. And here you can see the groups that interact with each other. So basically, this highlights the fact that interactions other than hydrogen bonds between side chains can stabilize or destabilize a helix. And R groups that are amino acids that are 3 residues apart can also interact with each other. And then this is shown an ionic interaction between ASP102 and ARG103 that's shown here. And again, these electrostatic interactions such as these also contribute to helix stabilization. So this is a cross-sectional and space-filling views of an alpha helix. So in C, what we see is if we're looking down the middle of the helix, it gives you really the false impression that the helix is hollow because the balls don't represent van der Waals radii of the individual atoms. But if you were to look at a space-filling molecule, this would be completely filled. This also shows the periodicity of the helix. And then this is the space-filling diagram here. helix periodicity can be shown in a helical wheel, and this helical wheel is shown here. This representation can be colored to indicate surfaces with specific properties. So in this case, these amino acids in yellow are hydrophobic. The amino acid in blue is positively charged and red is negatively charged. And so here we see that there are basically two sides of the helix. The right side is hydrophobic and the left side is hydrophilic. Now, because of this, helices make great adapter molecules because they can bind or serve as the bridge between a hydrophobic and a hydrophilic surface. Under most conditions, those two would not come into close proximity to each other. So because of resonance, each peptide bond has a very small electric dipole. This dipole increases with helix length because the 4 amino acids at each end don't participate fully in hydrogen bonding. So at the amino terminus, you have a partial positive charge, and at the C terminus, you have a negative charge. So there are a number of factors that affect the stability of an alpha helix. So first is this electrostatic attraction or repulsion between R groups of successive amino acids. And so you're really unlikely to have two negatively charged amino acids next to each other in an alpha helix. Additionally, there's the bulkiness of adjacent R groups. So very large amino acids tend to not be found in alpha helices. One example would be proline. Interactions between R groups that are spaced 3 to 4 amino acids apart. So there is periodicity to that helix. So R groups that are 3 and sometimes 4 amino acids apart have the ability to interact with each other. And so you might find oppositely charged amino acids at those positions, and they would tend to stabilize the structure. The occurrence of prolines and or glycines also influences helix stability, and so it makes sense that proline is not often found in helices because it's got that really large bulky side chain. But interestingly enough, we also don't see glycine residues in helices, and one of the reasons is that it's just too flexible. It's almost floppy, so it doesn't provide enough support to the structure. And finally, there are interactions between amino acids that are at the end of the helix. So the final, because remember how when we had that electric dipole, there was a positive charge at the amino terminus and a negative charge at the carboxy terminus. And as a result of that, you typically find negatively charged amino acids at the amino terminal end and a positively charged at the carboxy terminal end. And those, again, the opposite charges tend to stabilize the structure. So those are factors that contribute to alpha helix secondary structure. There's also beta conformation, and these can be found as pleated sheets or as beta turns. And so here we see a representation of an antiparallel beta sheet. So we see one strand on the top, and this is the N terminus and the C terminus, and then it's antiparallel, so this is going to be the N terminus and the C terminus, and the N terminus and the C terminus. So some things to point out as you're looking at the top of the molecule, or when you're looking at the molecule, is that these R groups are in alternating from one side of the sheet to the other. So here we see they're on the bottom, they're on the top, bottom, and top. They form a zigzag structure. So here we see that zigzag structure. The sheets are, or the strands of the sheet are lying next to each other, and they're stabilized by these hydrogen bonds here. And then these hydrogen bonds are in line with the atoms. Again, they're antiparallel, so they have opposite N and C termini, so N, C, N, C, and so forth. Now the repeat of beta sheets or antiparallel beta sheets is 2 amino acids have a 7 angstroms long, and so there's about a 3.5 angstrom per amino acid. So now if you remember, for the fully extended amino acids, there's about 3.6 angstroms per amino acid. So these antiparallel beta sheets are very extended, almost equal to a fully extended polypeptide. And in contrast, when we looked at those alpha helices, their amino acids were only 1.5 angstroms in length on average. And so what you see is a very compacted structure in the alpha helix as compared to the antiparallel beta sheets or the fully extended. So we can have parallel beta sheets, and again, as the name implies, these are parallel, so they have all of their N and C termini facing the same direction. Now the repeat unit is slightly shorter, so it's 6.5 angstroms per repeating unit per 2 amino acids. There are also numerous H bonds, but in contrast to the antiparallel, which were in line, these are distorted. Now typically they have very small R groups, so we see these R groups here, and they tend to be glycine and alanine, and so that is to allow the sheets to come into close contact with each other. So beta sheets tend to have high percentages of glycine and alanines, and if we look at silk, which is a classic parallel beta sheet, we see that 1/3 of all the amino acids are actually glycines or alanines. So we have antiparallel beta sheets. Now we're going to look at beta turns. So most proteins assume a globular shape, so there has to be some way for the polypeptide to make turns. And turns actually comprise about 1/3 of the total amino acids in a protein. So basically they serve to connect adjacent secondary structures like alpha helices and beta conformations. Now one of the most common is the beta bend, and this is a 180-degree turn, and it's comprised of 4 amino acids. There are 2 types of beta bends, a type 1 shown here and a type 2 shown there. And they're going to, type 1 is the most common, and they're going to differ a little bit in their amino acid composition. So if we look at the type 1, what we see in the second position is proline. In type 2, what we see is that there's typically a glycine residue at the 3rd position. So the carboxy terminal of the first amino acid right here is hydrogen bonded to the 4th. So we see that in both the type 1 and the type 2 turns. Now the R groups of the central 2 amino acids don't participate in any interresidue hydrogen bonding. And so we see 1 and 4 interact with each other, but 2 and 3 do not. And the same is true here. 1 and 4 interact, and 3 and 2 do not. So glycines and prolines, interestingly enough, often occur in beta turns. Glycine is small, and so it's flexible and commonly found as the 3rd amino acid in the turn, but proline can also be part of a beta turn. There is an interesting reason why. So, and we'll see that in the next slide. So prolines are often found in beta terns, and that is because proline is amenable to forming the cis configuration that is amenable to a very tight turn. And here we see the trans and cis forms of proline, and then here is the general representation here. For bonds other than, or for amino acids other than proline, less than 0.05% of them are found in the cis conformation. In contrast, when we're looking at proline, about 6% are in cis. And so again, it's not a whole lot that are in cis, but there is more than there are for other amino acids. And the thing to remember is that proline almost always makes a turn, but not all turns have a proline. So here are values of phi and psi for various allowed secondary structures, and it's been overlaid with the previous plot that we saw for alanine. So this large plot is alanine here. And what we see is that when you look at anti-parallel beta sheets, parallel beta sheets, when we look at the collagen triple helix that we'll think about in a minute, right, twisted beta sheets. So all of these have a much more constricted phi and psi angles. And that's because they're much more constrained in the physical structures that they can take. Now, one thing that's interesting is that in theory, with what we know about amino acids, left-handed helices are theoretically possible, but they've really never been detected yet. So right-handed helix is down here. Left-handed helix has not been observed, but would fall in this region of the Ramachandran plot. So this, again, is just to give you, just for your knowledge. I don't expect you to memorize anything. But there are different probabilities of amino acids occurrence in secondary structure. And so here, if we look at prolines, they're not very abundant in alpha helices or beta conformations, but they're present in a lot of turns, as is glycine. Tryptophan and isoleucine, isoleucine and valine aren't really found in beta turns very often. They're often found in beta conformations, and some of it is in alpha helices. But again, this just says that there are limitations imposed by the functional R groups that's going to influence whether or not a particular amino acid is in a particular structure. One interesting observation is that there are some amino acid sequences that can adopt two different conformations. And this is one example of this. So this is just a polypeptide, VDLLKN, and that's highlighted here. And depending on the amino acids that are around it, they can adopt either an alpha helix or a beta sheet. So what this tells us is that there are some amino acid sequences that don't specifically require a particular secondary structure. And so the tertiary structure, or the structure and the environment around the sequence, would most likely determine whether or not it is adopts an alpha helix or a beta conformation. So we've looked at primary and secondary structure, and now we're going to look at tertiary and quaternary structure. So remember that secondary structure describes spatial arrangement of atoms in a local region, and tertiary structure describes the overall arrangement of all atoms in a protein. And then quaternary structure refers to how subunits or different polypeptides are arranged into a single protein. So based on the number of subunits, in terms of quaternary structure, depending on the number of subunits, you can have a dimer, which would be 2 molecules, trimer, tetramer, hexamer, octamer. And if all subunits are the same, that would be a homodimer, a homotrimer, and so forth. And if they're different, it would be hetero. So there are a number of non-covalent interactions that stabilize protein structures. So we see hydrogen bonds, and we've talked a lot about them. We have ionic interactions, so this is the attraction of different charges or the repulsion of the same charges. Also, we have hydrophobic interactions, and so this is basically the force or the tendency of hydrophobic residues to kind of distance themselves or bring themselves away from polar solutions. And then there are van der Waals interactions, which include any two atoms in close proximity. So they just tend to repulse. There's a repulsion force that doesn't allow them to get closer than a particular distance. So all of these are very weak interactions. They take place at a distance of 3 to 4 angstrom. But the cumulative effect is really significant. So you have many, many hundreds of these hydrogen bonds and ionic interactions that together have a large stabilizing effect. If we look at the energy of dissociation for the different groups, hydrogen bonds, to break them apart, is between 2 or 5 kilojoules. Ionic interactions are a bit stronger. We're looking at 15 kilojoules. Hydrophobic interactions are similar to hydrogen bonds, so between 2 to 5 kilojoules, and then van der Waals reactions about 4 kilojoules. So again, the take-home message is that they are all weak interactions, but there are many of them, so the cumulative effect is quite dramatic. So when we're looking at tertiary and quaternary structures, we're going to talk about 2 types of proteins that are going to be classified on the basis of their conformation. So first we have fibrous proteins. So these are found in long strands or sheets. They typically have one type of secondary structure. So they're all alpha helices or all beta sheets. And they tend to be structural or extracellular. So if we look at some of the properties of these fibrous proteins, we see a chart here. We have the structure, the characteristic, and then the examples of occurrence. And so here we see an alpha helix cross-linked by disulfide bonds is the structure. These structures tend to be tough and insoluble. They provide protective surfaces or structures of different hardness and flexibility. And some examples of that are alpha-keratin of hair, feathers, and nails. Beta conformation, they tend to be soft, flexible filaments. So one example of this is silk fibroin. And then there's a collagen triple helix, which is a structure that typically is high tensile strength without stretch. And then one example of this is the collagen that you find in tendons and bone matrix. So alpha-keratin. So a couple of characteristics. First, almost the entire dry weight of hair, wool, nails, claws, horns, hooves, and much of the outer layer of skin is made up of keratin. It forms a right-handed alpha helix, and 2 of those helices associate in parallel in a coiled coil, and we'll see a figure of this in the next slide. So it amplifies strength characteristics of the molecule and acts almost as a rope. They have a primary repeat of 5.4 angstroms, and it's different from the standard alpha helix because of its coiled nature. Now we see the association between the two right-handed helices are left-handed. The surfaces of the helices that interact are rich in hydrophobic amino acids like alanine, valine, leucine, isoleucine, methionine, and phenylalanine. And these R groups mesh together in a very regular interlocking pattern. So the tertiary structure is dominated by right-handed alpha helices with left-handed superhelical twists. And the quaternary structure, coiled coil, associates to form very large complexes like hair fibers, and this strength is enhanced by disulfide bonds. And so just as an anecdote or an interesting fact, 18% of the amino acids in rhinoceros horn are cysteines that are involved in disulfide linkages. And basically you get this hierarchical structure formation. So you get a coiled coil, bunch of coiled coils form a protofilament, and protofilaments combine together to form protofibrils, and so on. The higher order structure of keratin. So we have this alpha helix. Two alpha helices come together to form a two-chained coiled coil, often called that left-handed superhelix. These come together to form a protofilament, which then associate into protofibrils, intermediate filaments that we see then take up the entire cell. So permanent waving is based on changes that occur in structure when disulfide bonds that hold this keratin together are reduced and oxidized. So when you heat hair, when you expose hair to moist heat, it can be stretched. And basically what happens is that at the molecular level, these alpha helices are stretched out until they arrive at that fully extended beta conformation. And this characteristic, upon cooling, they spontaneously revert back to that alpha helical conformation. So the characteristic stretchability of alpha keratins and their numerous disulfide linkages are the basis of permanent waving. So basically a solution of a reducing agent is applied with heat. The reducing agent cleaves the crosslinks by reducing each disulfide bond to form two cysteine residues. That moist heat breaks oxygen bonds and causes the alpha helical structure of the polypeptide chains to uncoil. After a time, the reducing agent is removed and an oxidizing agent is added to establish new disulfide bonds between pairs of cysteine residues of adjacent polypeptides. But these are different pairs as were formed before. So after the hair is washed and cooled, these polypeptide chains revert to their alpha helical conformation. And the hair fibers now curl in the desired fashion because the new disulfide cross-linkages exert torsion or twist on the bundles of the alpha helical coils in the hair fibers. So the same process can be used to straighten hair that's naturally curlied. So a permanent wave or hair straightening is not truly permanent because when that hair grows back, a permanent wave or hair straightening is not truly permanent because the hair grows. In the new hair replacing the old, the alpha keratin has the natural pattern of disulfide bonds. So here we see the disulfide bonds, you add the reducing agent, you then see cleavage of these into the individual cysteine residues, the hair is then curled, and then when you oxidize the protein, then you get reformation of a different set of disulfide bonds. And so here you can see that the secondary structure of the first molecule and the last is very different. So collagen is the next fibrous protein that we're going to discuss. It is the most abundant protein in the human body, and it constitutes up to 30% of its protein mass. Now, mammals have more than 30 different structural variants of collagen. It is part of the extracellular matrix proteins that play a dominant role in maintaining the structure of different tissues. And They also mediate cell adhesion, chemotaxis, and migration, so cell movement in response to different cues. Collagen consists of 3 polypeptide chains and contain at least one domain composed of the repeating sequence GlyXY in each of those constituent chains. And now, when we look at collagen, sometimes all 3 chains are identical, but sometimes there can be 2 or even 3 different chains. Glycine is found in every 3rd position, and that's essential to maintain that coiled-coiled packing. So if we remember, glycine is a very small amino acid, and so the coils can come very close to each other. The X and Y amino acids are anything other than glycine. A lot of times we see proline as the X position and 4-hydroxyproline in the Y position. These 4-hydroxyprolines are essential for the stability of the triple helix. So collagen consists of 3 helical polypeptide chains. It's a very large molecule. It's 3,000 angstroms in length, but it's only 15 angstroms in diameter, and it's about 1,000 amino acids long. So here we see a couple of representations of collagen. Here is one helix. So we see here that this ribbon diagram highlights the different side chains. So this is proline, and then we see the very small side chains in glycine. This is a space-filling molecule, or a space-filling model of one of the chains. And then here we see the 3 chains that are coming together. So we have the gray chain, the light blue, and the dark blue. So these are left-handed helices. They're not alpha helices. They have different dimensions. And they come together to form a right-handed superhelix or supertwist. And you can see here in this representation how closely the different helices are associated with each other. So here, if we look down into the middle of this superhelix, what we can see, again, the same coloring here is that we have the gray, dark blue, and light blue. So those are the 3 different collagen chains. And then what we see here in red are those glycine residues. And you can see here why this has to be glycine is that they're packed so tightly into this helix that really no other side chains would be amenable to this folding. And then these proline and hydroxyprolines are seen kind of on the outside of this helix, and they are found because they really are amenable to forming that sharp bending. So we talked in the previous slides about how they can form that cis conformation, and that allows them to fit inside of this helix. So every 3rd amino acid is glycine in collagen. There's really not room for anything else in the center of this triple helix. So here we see each helix, so the red, blue, and yellow, and then we see the glycines on the inside of that molecule. So these 3 alpha helices are hydrogen bonded to one another. These hydrogen donors are amino groups of the glycine on one chain, and the acceptors are the carbonyl groups of the residues of the other chains. Now, I mentioned earlier that scurvy is a defect in collagen. That's the result of a lack of vitamin C. Scurvy leads to general degeneration of connective tissue. It results in hemorrhages of fragile blood vessels, tooth loss, poor wound healing, bone pain, and then here are some lovely images of some of the symptoms. So here we see receding gum lines and tooth loss. Here we see pale skin, sunken eyes, loss of teeth, and this comes from a handbook that sailors use to kind of diagnose the different symptoms of scurvy. So proline can be found in two conformations, so the endo and the exo conformation. So collagen structure requires that the proline at the Y position be in the exo conformation shown here, and this hydroxylation at the C4 position stabilizes this structure. So it also requires that the proline in the X position have the endo conformation, and in this case the presence of the hydroxyl would destabilize the structure. So typically at the X position you have the endoproline, and at the Y position you have this hydroxylated proline. And as I mentioned, vitamin C is required for this process to happen, this hydroxy proline production, and if you don't have that, you have defects in collagen and defects in connective tissue. So here is electron micrograph of collagen fibrils, and we can see here that they form these long, thin structures that are striated. The collagen superstructures are formed by cross-linking of these collagen triple helices to form collagen fibrils, and we can see that here. So these are the individual collagen molecules, and we can see this staggered nature of this, and so this staggered group leads to that striation. And then these cross links that you see between the collagen fibers are covalent bonds between lysine or histidine amino acid residues. And then here you just see the cross section if you were to look at a single collagen molecule. So silk fibroin is the last structural molecule or fibrous molecule that we're going to talk about. It's the main protein in silk from moths and spiders. It is composed of an antiparallel beta sheet structure. There are very small side chains of alanine and glycine that allow these sheets to closely pack, and this structure is stabilized by hydrogen bonding within sheets and then London dispersion interactions that occur between sheets. And then here we see the antiparallel beta sheet, so that antiparallel nature is denoted by the directions of the arrows. Each sheet is designated by a different color, and so we have red, blue, and green. And here we can see these glycine and alanine residues that are necessary. So these are very small amino acids that allow for the very close packing of those sheets. So again, silk is rich in alanine and glycine, and it involves close packing of beta sheets. And this structure is stabilized by hydrogen bonding. And what you'll notice when you play around with silk is that it's very flexible, but it does not stretch. So spider silk is used for webs, egg sacs, and wrapping of prey. It's extremely strong material. It's stronger than steel and can stretch a lot before breaking. And it is a composite material, so it has crystalline parts and then rubber-like stretchy parts. So it's very versatile. People are looking at using spider silk for protective clothing because it's actually stronger than Kevlar, and it has a lot of very versatile structures or purposes. So we've talked a little bit about fibrous proteins, and so just a reminder, they're long strands or sheets. They are typically composed of one type of secondary structure, and they're typically structural or extracellular proteins. So the next class of proteins we're going to look at are globular proteins. So these are compact, spherical or globular proteins. There are typically multiple types of secondary structure, so you'll see alpha helices and beta sheets in a single polypeptide, and they are also, enzymes are typically globular, and also regulatory proteins. So we can see here, this is an example of the relative sizes of each of the different types of molecules that we're looking at. So if you had a beta conformation, if you had a protein of a given size, so in this case, the protein is BSA, or bovine serum albumin. If you had that in an extended beta conformation, you would have a molecule that's about 2,000 angstroms long and 5 angstroms in width. If this were alpha helix, it would be shorter, about 900 angstroms, and fatter, 11 angstroms in width. And then if you were to have a native globular form, it would be a much more compact structure, and it would be, this is just one example, 100 angstroms in length and 60 angstroms in width. So a much more compact molecule. And this is just an example of a globular protein. This is hemoglobin. This is the ribbon diagram that kind of accentuates the fact that there are multiple alpha helices that are packed in on each other. This is the porphyrin ring here. This coordinates the iron. And then here we see a space-filling molecule, or a space-filling model of the same molecule. So this is just a closer lookup of this. So there's myoglobin is 18 kilodaltons in size, and the globular protein is 10-fold smaller than if it were fully extended in that beta sheet. There are 8 alpha helices, and these alpha helices comprise almost 70% of the amino acids in hemoglobin. And again, it's a heme protein. So this is a conjugated protein. We talked about that before. And the prosthetic group is the heme group. This also highlights some important forces that are involved in the stabilization of hemoglobin or myoglobin. And what we see here is that we have the hydrophobic residues are on the inside of the molecule. So these hydrophobic residues are shown in blue. They tend to be inside the molecule. So here if we see the space filling, most of the polar amino acids are facing the aqueous solution. So in an aqueous environment, protein folding is driven by this tendency of the nonpolar amino acids to be excluded from water and buried on the inside. And this is just to show that lots of different proteins form this globular structure. Here we see the contour modeling, the space filling, and then we see the ribbon diagrams. And so on the bottom, we kind of see this representation highlights the different structures. And so we have alpha helix, alpha helix, alpha helix, alpha helix. Here we have some beta sheets. Disulfide bonds are shown in yellow. And then some of the amino acids that are important in catalysis are shown here in red. And then also shown here in the contour diagrams. So, you know, all of these are different. There's a diverse structure that we see, lots of different structures, but they all are fairly compact and tend to be globular.